Welcome to the Monoxivent webinar series. We apologize, we're getting off to a bit of a late start this morning, so we'll try and keep it short, straight to the point. My name is Brian Phipps. I'm an engineer at Monette. I'm here with Sam Stelzner, our other engineer, and Erik Swanson, the division manager of Monoxivent. Today's presentation is going to be focusing on Monoxivent's fan selection and how to select a proper fan for your application. A little bit of housekeeping before we get started. In the lower left corner of your screen, there's a chat window, and at any time during the presentation, we encourage you to ask all your questions in that chat window. Now, we'll do our best to get to all the questions that are asked. If your question isn't asked, rest assured, we will keep a copy of it, and we'll contact you at a later time, especially if your question requires a significant amount of detail or maybe some research to answer. And without further ado, I'll turn it over to Erik.
Thanks, Brian, and thank you all for attending the seminar. Today, we will be talking about fans, and these are going to be primarily the fans that we offer for our systems and that are appropriate for our systems as well. Obviously, what we need to know before we can even select the fan is the performance, the required performance for the system. That would be both CFM in regards to airflow and static pressure, what the fans will be working against. In our case, at least for today's discussion, we'll talk about vehicle exhaust systems and welding exhaust systems and some of the CFM requirements for those particular types of systems. For example, in the vehicle exhaust, 4-inch diameter hose, 300 CFM per drop would be appropriate for an automotive like a Chevrolet garage or something along that line where they're doing general tune-up type work. We get into 6-inch diameter, 600 CFM per drop. That would be more along the lines of over-the-road semis or some industrial equipment. 8-inch diameter, 1400 CFM per drop, and that we see a lot in the military applications. They ask for a higher airflow. Now, with that said, in the vehicle exhaust systems, as well as with the welding exhaust systems, we like to size our main ductwork for 2,000 to 2,500 feet per minute velocity. That is, why would that be important? It's because that can add to the static pressure losses in the system. Once you know what your velocities are in the ductwork and how many twists and turns you have through the various sizes, you'll be able to calculate out how much static pressure loss there would be in the duct system. Same thing with the welding exhaust. We know we need about 600 to 700 CFM per drop for the 6-inch arms and about 1,100 to 1,200 CFM per drop for the 8-inch arms. Now, with that said, once we can add up how many drops we have at what CFM, we can come up with our total system CFM. And once we take a look at the duct system, the duct layout, then we can calculate what the static pressure losses are going to be for that duct system. Some of the things to consider for static pressure are not only the ductwork, but the hose diameter, arm diameter, and the hose or arm length. Those can have an effect on what the static pressure loss is going to be. The ductwork off the discharge of a fan, that can also affect how much static pressure we have on the fan. Some other considerations would be things like louvers, discharge louvers, dampers that might be in the duct system, altitude, airstream temperature, those kind of things can affect what the system static pressure is going to be. Also, some poor duct design. If there's odd elbows or elbows that go against the grain, so to speak, those can add static pressure. It's called system effect. Bad duct design adds extra static pressure, which in turn adds more horsepower to the system. Once we've determined what the CFM is going to be, as well as the static pressure, then we can move on to selecting a fan. The first fan that we have here is our D-series blower. It's a simple cast aluminum wheel, cast aluminum housing, and a drive motor. Very simple. These are, the motor is a UR labeled motor, meaning it's recognized by UL as an electrical component for a system. However, these fans are not UL listed as an assembly. Again, there's 4 basic components to the fan: the motor, the upper and lower housing, and the fan wheel. In addition to that, we have the mounting brackets, but the basic components for the fan are those 4 pieces. We have half horse, 1, 1.5, 2, and 3 horsepower motor options on these, as well as a variety of different housing sizes. We can mix and match the housings to give you the performance that you want that we'll see in a later chart. These fans are available in single phase, 115, 230, or 3-phase, 208, 230, 460, and 575 volt. Performance-wise, if you remember the chart, the first chart we looked at performance, you look at the half-horse fan, that's pretty much appropriate for a single 4-inch drop, for example, or a 4-inch arm. The 1-horse and 1.5-horse fans would be appropriate for a 5 or 6-inch diameter drop. The 2 and 3-horse you could use for an 8-inch arm or possibly a single 8-inch hose drop, or even multiple smaller hose drops in terms of CFM. Now you can see in a couple spots there, especially on the D10 and the D20, there's some dashed lines under certain static pressures, 1, 2, and 3-inch in the case of the 1-horse and the 1 and 2-inch for the 2. These are radial bladed fans, and if they don't have, in those horsepowers, if they don't have enough load on them, they will overload, they'll overamp. So you want to make sure that we have enough static pressure for the 1-horse, especially in the 2-horse, so that we don't overamp those motors. It's a simple fix. If you have one in the field that might be overamping, you can put a blast gate on the discharge of it, add a little more static pressure to the system, and we can get the amps back in line. But just be aware that when you are selecting these fans, watch the static pressure versus where these will fall on the curve, so we don't just put a fan in the field that might overamp. These fans are available with ODP motors as well as explosion-proof motors. Because the wheel and housings are aluminum, they're spark resistant right out of the gate, so they're pretty safe that way. The D-series fan can be ordered with a simple wall mount bracket like you see here. We can also do a foot mount base if you want to mount it on the wall bracket or something like that independently. We can put connection flanges on them so they will mount directly to a hose reel. We call that our DMS or DMHR version of that particular fan. We'll put a flange on the inlet of the fan and a corresponding flange on the discharge of the hose reel, and it's a simple bolt-up operation. And finally, we can do this same fan with a special bracket to mount it directly to an arm. And that could be not only for the internally supported arms, we can mount them on the tube type arms as well. Then if we get out of the range of performance for the D-series fans, we move into our BI series blowers. These are a belt drive, backward inclined centrifugal vent set. Pretty bread and butter item there. They are typically class 1 construction, which is good to about 5.5 inches of static pressure. They are powder coated straight from the factory. They are belt drive bearings. They come standardly with a weather cover. And normally we put a discharge damper on it, a gravity discharge damper. The motors are standardly ODP. However, they can be done TEFC if required, as well as explosion proof. We can do optional coatings as well, phenolic coatings or high temperature coatings if we get into a high temperature application, as well as some of the other accessories that we might put on it for high temp applications like heat slingers, insulation, that type of thing. This is a fairly butter item. If we start getting into extreme high static pressures, we might have to convert this to a class 2 construction, which is a little heavier construction, but it can handle higher static pressures. And beyond that, we would move into what we call our MHA. It's an industrial backward inclined fan that can handle even higher static pressures yet and some higher temperatures if required. This is the standard performance chart that you'll see in our catalog. This happens to be a BI 120, I believe, a 12-inch diameter wheel. And you can see with these fans that when you're in the lower static pressure ranges, you have a fairly wide range of choices in terms of CFM. Now, the farther right we get onto that chart, you can see that it gets pretty narrow. As our static pressure goes up, the operating range of the fan tends to go down, and the RPM tends to go up. The brake horsepowers that you see there are without drive losses, so you need to add a little bit for drive losses when you're selecting the horsepower for these fans. Again, like we talked, we can do these in Class 2 construction if need be. We can do what we call an MHA industrial type fan, much heavier construction. We do have some inline fans available. However, as you fan guys know, a lot of the inline fans are not real kind with static pressure. You start getting your static pressures higher, and the inline fans just, they don't like to perform with high static pressure. Again, we can do high temperature construction. We can do optional finishes. Vibration isolation, we have a wide range of those available for these fans, anywhere from just standard rubber and shear all the way up to house spring and hanging spring if need be. We can do isolation bases if we have to, that type of thing. Explosion proof is an option for many of these fans. We can do from a simple aluminum wheel and a rub ring up to all aluminum construction if we have to, as well as explosion proof motors. Some of the other accessories that we can provide with these fans would be a wall mount, UFP, universal wall mount platform that they can mount the fan on, or a universal hanging platform that they could hang the fan from. We can do tapered inlet and tapered discharge connectors. We can do flexible connections. We can do low loss stack heads if required. And all these are available, and a lot of these accessories that you're seeing here are in our catalog as well as in our pricing as well. We can do starter boxes as well for 3-phase or single-phase. Now, a lot of times the electrical contractor provides these, but we have seen instances also where we are asked to provide them. We can do these. Again, primarily it's for 3-phase power, but we have done some for single phase. The standard box is a NEMA 12, which is good for indoor mounting. We provide the transformer, the contactor, the overload, and the terminal strip inside the box, and a simple on-off switch in the door. This is the wiring diagram for that. Internally, it is totally wired up, so there's no internal wiring that has to be done other than to bring your main power in, the L1, L2, and L3, as well as the power out then to the fan motor, which would be on 2, 4, and 8, it looks like. Now, we have had, we get more and more requests for these every day, and especially from the colder climates and the real hot climates, that people are asking for variable frequency drives. In our opinion, that they tend to look good on paper, but when you really look at what has to be done, you need to pay attention to not only the fan selection, but your duct layout if you want to use a VFE and have it be effective and have it work properly. Fan selection is very important with these. I'll be showing you some performance charts here that kind of drive that point home. Duct sizing is important to maintain proper transport velocities. If we size our system like we talked about earlier for 2,000 to 2,500 feet per minute at full airflow, what's going to happen to that transport velocity is we slow the fan down. For us, we do not want that transport velocity to vary much. We want to try to keep it fairly consistent. You will need dampers or some way to shut off the drops that are not going to be used. We're going to have 10 drops in a system, and we wanted to be able to shut some of those off so that we could slow the fan down and save some energy. We really want to make sure we put dampers in, as well as make sure that the people that are using the system use those dampers religiously. A lot of times what will happen is you have dampers in all those drops. They're either going to be all open or all closed, and nobody's paying attention to what's going on. Also, something to consider if variable frequency drive comes up in the conversation, if it's a smaller system, not too many drops, they really might want to consider using multiple smaller direct mount fans and just operating the fans independently rather than going through the expense and control nightmare of doing a variable frequency drive. The variable frequency drive itself is a very simple thing. I'm sure a lot of you guys already have frequency lines. This is a pretty simple unit, and for us, with variable frequency drives, the systems are typically controlled by a static pressure sensor. What that means is we set that static pressure sensor for a certain static, and let's just pick a number. Let's say it's 5 inches. So as when you turn the system on, if all the dampers in this case are open or all the hose drops are open, the variable frequency drive is going to really should be driving the fan to its full CFM performance at 5 inches of static pressure. As the dampers go closed, obviously the static pressure is going to go up, which is going to tell the variable frequency drive, hey, I need to slow down to get my static pressure back to 5 inches. So as the static pressure changes in the system, the VFD is always going to hunt for that, whatever specific static pressure we set the static pressure sensor up for. We'd like to get the static pressure readings at the end of the runs rather than in the main line up to the fan. That way we get a good average of what's going on in the system as a whole rather than what's going on just in that one section of duct. Now, fan selection, again, is important in this case. If we looked at the BI fan, for example, here with the 5-inch static pressure, if we look at that chart on the top, you'll see that the range for 5 inches static pressure is only 3,900 to 4,500 CFM. Anything in the white lines where it says unstable in red and below, the system is unstable. The fan will surge in that area. It's not that it's not going to move air, because it will, but it doesn't know where to stop or start. So it's going to be surging around in those areas. So when you look at that BI fan, for example, right there, the effective range at 5 inches, if that's where we're setting our static pressure sensor, is only 600 CFM. You don't get a lot out of it. So if we want to make sure that we get a fairly decent range, we need to look at a different fan. In this case, we look at the MHA fan. I believe that's a 110. And you can see that the range at 5 inches is 1,800 to 7,800 CFM. We have a much wider range there. Not that you want to pick it wide open or have it in this case, but really what we're looking at is how much it will turn down, how far we can get it to turn down. In our case, we got to look at how many drops are on the system, how much CFM is each drop, and that will kind of tell us how far down or how many drops we can turn this thing down to before it's going to fall into the unstable part of the curve. But in this case, if somebody asked for a VFD, I would direct them towards the MHA type fan because we have a much wider range. Now, something else to consider here, the whole purpose of selecting a VFD and doing that type of a system is to save energy, to not only minimize the amount of air that we have going out of the building, but to minimize the amount of horsepower we're burning. If you look at the BI fan up top at 5 inches, you know, the horsepower is, you'd probably select a 7.5 horsepower fan in that case. If you look at the MHA fan, if we wanted to get the full 7,800 CFM out of that, we'd need a 40 horsepower motor. When you look at it that way, are we really, truly saving energy? Are we saving money? Are we trying to, you know, are we getting what we think we're going to get? If we got to put a 40 horsepower motor on it, maybe it's really not the way to go to do a VFD. So those are some things that you really need to consider when you're doing this.
Thank you, Eric, and thank you to our attendees out there. We know your time is very important, and we appreciate you taking time to spend with us this morning. This webinar and all of our previous webinars are available on our website at www.monoxivent.com. Click on the Resources tab and click Webinars. You can also find them on our YouTube channel. Just go to youtube.com and search for Monoxivent USA. Next month's webinar will be held on fiberglass products. And again, if any of you submitted questions that we didn't have time to get to, feel free to email or call any one of our design staff here at Monoxivent. We're not only here to help you go through the catalog and help you with pricing, but also help design the projects to begin with. Thank you.